For our first line integral of a vector field, let's see if we can figure out how to measure how much a vector field flows along a curve. So as an example, let's draw a curve that maybe goes from here down to here. Maybe that's too long. Let's go from here. Actually, no, that was fine. Let's go from here to here. Now, at some points along this vector field, at some points along this curve, let's traverse the curve this way. At some points along this curve, the vector field is flowing against the direction that we're traveling in. And those should contribute negative flow, right? And down here, where the vector field is pointing in the direction that we're traversing the curve, those should count as positive. So flow in the direction of travel should count as positive. Also, these places where the vector pointing against our direction of travel is longer, those should count for more than these places over here where the vector pointing against our direction of motion is smaller. So faster flow should count for more. So flow in the direction counts as positive, and faster flow counts for more. But if you think about it, we already have a way of measuring this if we have two vectors. Right? If we have two vectors, the dot product will sort of do these two things. The sign of the dot product, if you remember, the sign of the dot product tells you whether two vectors are pointing mostly in the same direction or mostly in opposite directions. And the magnitude of the dot product is some mixture of the magnitudes of the individual vectors and, of course, the cosine of the angle between them. So if we can just come up with appropriate vectors to use, we should be able to measure the amount that the vector field is flowing with or against our direction of travel at a single point. Of course, if we can measure how much the vector field is flowing with us or against us at a single point, then we can just do a line integral to add up the total. So let's focus on just a single point. So at one point. So we need to be able to measure, so we have a vector field at that one point, and we need to be able to measure whether it's flowing with us or against us, right? So what we really need is, right, at this point we have a vector coming from the vector field. What we need is another vector that counts as our direction of travel. Right? What we need is a little vector pointing in the direction that we're going. And you might think that, well, r prime points in the direction that we're going, but the problem is r prime contains information not just about the direction we're going, but also how fast we are moving in that direction. And how much the vector field flows with us or against us shouldn't have anything to do with the particular parameterization of this curve. So r prime itself isn't quite the right idea. What we need to do is keep only the direction information about r prime and throw away the speed information. And the way to do that is to turn r prime into a unit vector. So let's just divide r prime by its own length, like this. So we'll take the dot product of these two vectors. Right, now let's just check, incidentally, this vector, r prime over the length of r prime, this has a name. This is called capital T. This is the unit tangent vector for the curve. So this depends on the curve. Right, so it depends on r. Okay, so we're going to use f dot capital T as the dot product that will measure this at a single point. And just to check that it satisfies these two quantities, if f and t are mostly in the same direction, so if f and t are pointing mostly in the same direction, this dot product will be positive, and that's what we want. If f and t are pointing mostly in opposite directions, then this dot product will be negative, which is the opposite of what we were asking for, so that's good. Also, let's check that faster flow counts for more. Well, if we make f longer, then this dot product will get bigger because, right, if you stretch one of these factors, the dot product is increased by the same amount. So faster flow will count for more. So this dot product does appear to be measuring what we want at a single point, and of course it's a scalar. Right? The result of a dot product is a scalar. So what we should do to measure the total flow along this curve is just to do the line integral of this quantity along the curve. So for the total flow, we will just do the line integral across the curve of f dot capital T ds. Right. So this is our normal scalar line integral, but the scalar function that we are integrating is actually itself a dot product. All right. So this is a fine idea, right? Remember when we've seen this once already, when we have a new idea for a type of integral, usually we will need to write down our idea for it and then figure out how to parameterize it. Right? We did that with our scalar line integrals. So this vector line integral, this is our idea for it, but now let's actually parameterize it to see what happens. So when I say parameterize it, remember that we're going to have a parametric curve r of t that traverses our curve c in the appropriate direction, in the positive direction. Okay, so when we did this, right, we get some bounds coming from the parameterization that tell us what what values for time cause us to trace out this curve. Our vector field needs to know where we are at every time, and it's the parameterization that tells us where we are. So f of r of t. The unit tangent capital T, that depends on where we are along the curve, which depends on the parameter t. Right? So remember that capital T is r prime over the length of r prime. R prime, since r prime is a function of time, little t, that means capital T is also a function of time, little t. So we put time here. And then ds, well, remember ds is the magnitude of r prime times dt. Okay. So this is the big mess that we get when we parameterize this integral. But actually something nice is happening. Look up here, capital T is r prime over length of r prime, but here's the length of r prime. So if we sort of unpackage capital T, we get the integral from a to b of f of r of t times, or dotted with r prime of t over the magnitude of r prime of t times the magnitude of r prime of t dt. And then we can simplify this. So this is the integral from a to b of f of r of t dotted with r prime of t, r prime of t dt. So it looked very complicated at first, this flow integral that we're inventing, but once we simplify things, it actually isn't that bad, right? So normally, if I need to write this down, I'll do a little shorthand. We'll just remember that the parameterization is here and that time is the independent variable, and I'll just write f dot r prime dt. So that's how I'll normally write this. But actually, there's an even nicer way to write this, which is this. So, right, r is a function of t. It's really r of t. And that means that the differential of r should be the derivative of r with respect to t dt. Right? But derivative of r with respect to t, that's just another name for r prime. And here we have r prime dt. So this chunk right here is actually just dr. So this is the integral from a to b of f dot dr. Now it looks a little bit weird to have a differential that is part of a dot product, but this differential is actually a vector, right? R is a vector. It's a vector valued function since it's a parametric curve. So this differential dr is actually a vector thing. It's like d of something is like an infinitely tiny chunk of something, and so dr, since r is a vector, an infinitely tiny chunk of it is a vector thing, an infinitely small vector kind of, but a vector nevertheless. So now we have three ways of writing this, three decent ways of writing this flow integral. Our original idea, which is notation that we will keep when we need to mention flow integrals in general. So the integral over the curve of vector field dot unit tangent ds. And then two ways of expressing what this turns into when it's parametrized. The first way is this, f dot r prime dt, and the second way is this, integral of f dot dr.